Right, thank you. Thanks for the invitation to speak at this conference, and for the talks that have already been given so far. They've been great. Everything I'm going to say today is joint with Tiago de Paiva, who is a junior person here at Monash University. Someday, if we can travel again, you should have him come and visit. So the title of my talk, as you can see, is Satellites and Lorenz Links. So the first part of my talk, I'm just going to give a little bit of background on the problem. And then for the second part of my talk, I'll explain a little bit more of some constructions. Background, 1963, a meteorologist named Lorenz wrote down a system of equations that he used to describe some weather patterns. And here are the equations. This is copied out of a survey article. If you run numerical simulations of flows for this system, then they appear to live on a branch surface. This picture at the top of the screen is such a numerical simulation. And then this was proved. So this was confirmed by Guggenheimer and Williams, and then Tucker proved it rigorously. And here is the branched surface of a Lorenz knot. I've stolen most of my figures in this talk from various papers. I put some credit on the side. So every Lorenz knot now, or every periodic orbit of this Lorenz system lives on this butterfly type surface, and it can be described by a braid in L's and R's that's closed up with these two petals. So what this means is that the periodic orbits now are knots in the 3-sphere. And so in 1983, using the fact that now we have this template, Berman and Williams started studying knot theoretic properties of these periodic orbits. This is a figure from their paper in 1983, where they have drawn 3 different periodic orbits of this system on the template, and then they've been able to identify the knots that are involved. So you've got a trefoil knot, a torus knot, and a Purcell knot, all contained in this template. So this was 1983. Around the same time, William Thurston was looking at geometric types of knots. So he had a bulletin article that showed that a knot complement in S3 is either a torus knot or a satellite knot or hyperbolic. And so Berman and Williams looked a little bit at this, these possibilities. From their 1983 paper, they showed that every torus knot is a Lorenz knot. And then they also, looking at satellite knots, they were able to find some satellites. They found that if you have a Lorenz knot with crossing number C, any arbitrary coprime integers, then you can build a satellite that is an A prime plus AC cable on the Lorenz knot. And they kind of did this just by putting a tube in the Lorenz template and sticking this appropriate knot inside the cable. Okay, so let's do a quick review of some of the terminology here. So some definitions. Let me just scroll a bit. A satellite knot. So when I'm talking about satellite knots, you start with a knot P inside of a solid torus, and then you take this whole solid torus and you embed it into a neighborhood of another knot that's sitting inside of S3. So you have P is called the pattern. You have a companion is C, so 2 knots. You stick the pattern inside a neighborhood of the companion, and you call the embedding F, and then the satellite knot is F of P. So this, for example, I stole this from Wikipedia. This is an image by Ryan Budney. In this case, we have a satellite knot. You can see that this knot runs around a tube, and the tube crosses over itself 4 times in an alternating fashion. That's a figure 8 knot. And then this pattern, this is just a clasp inside the solid torus. So if you were to put that in S3, it would just be an unknot, but this is a Whitehead link. And so if we're talking about a cable knot, this is just a special type of pattern. In this case, P is isotopic to some sort of a PQ torus knot. Okay. Okay, so there is a conjecture that is attributed to Morton, and we found this in a survey paper of Pierre Tournois, nodes de Laurent, in 2011 is when this was published. And so he says this is personal communication. It's in French. If my French is correct, what he's basically saying, the conjecture is that every Lorentz knot that is a satellite is a cabling of a Lorentz knot, similar to the above result of Berman and Williams that I discussed. It has a different number in his paper, but that's what that's referring to. Okay, so a main result today is this conjecture is not quite correct as it is stated here. So in particular, from my paper with Tiago on the archive, our main theorem is that we can find infinitely many Lorentz knots that are satellites, but these are not cable knots. And the way that we prove this is we find the JSJ decomposition. There's exactly one essential torus. If you cut along this, both components that fall out are hyperbolic. And so you cannot have a cable on one side. Okay. Okay, so the conjecture was never really written down by Morton. He had a student, El Rifai, who was looking at satellites as well, who had come up with something similar, but with some extra twisting involved. So we're going to update Morton's conjecture. This also is following a question that was asked in this paper of Berman-Kaufman that I believe was 2009. And we're calling it the Lorentz satellite conjecture, which is we're going to conjecture that a Lorentz knot that is a satellite has companion Lorentz knots, and its pattern when embedded in an unknotted torus in S3 is equivalent to a Lorentz knot in S3. Okay, so not too far off. Basically, it seems that these Lorentz knots that are satellites, the companion is a satellite, and the pattern is not. The companion is a Lorentz knot. The pattern is not necessarily quite a satellite knot until you put it in S3, and then you can perform something to make it equivalent to a Lorentz knot is what it seems to be happening here. Okay. All right, so that's our new conjecture. So my plan for the remainder of the talk is just to give evidence for this and a proof of our theorem 1.1. We have two different ways of constructing satellite Lorentz knots. If I have time, I'll say something about hyperbolic Lorentz knots. So we want to show that this conjecture, it's an if and only if statement. So we already know that all torus knots are Lorentz knots. We want to say something about satellite knots and the hyperbolic knots to prove the conjecture. Okay, the constructions I think are quite fun. Construction 1 uses some cool techniques. First of all, an observation by Berman and Kaufman from 2009 that every Lorentz knot is equivalent to what they call a T-link. And I'll explain what a T-link is in a second. And then the second part of this uses this really clever satellite construction of Lie for twisted torus knots that you can apply almost directly for these T-links. So a T-link, what is that? And as I said, this is due to Berman and Kaufman 2009. You pick a sequence of positive integers, so 2 less than or equal to R1, less than R2, and so on up to RK. And then for each of these R's, you pick an integer S, it's a positive integer. And then you have these pairs, R1, S1 up to RK, SK. And your T-link is the closure of this positive braid built out of this braid word. It's basically little bits of torus links. So let me just maybe sketch on the side. If you have R1 strands coming in, this first product in the braid says R1 strands go in, and then you have S1 strands crossing over. And then second term here says you put in more. So now you've got R2 strands going in, and you've got S2 strands crossing over, and so on and so on and so on, up until you have, at the end, you've got this full bit of a torus knot. So this is a generalization of a twisted torus knot. If you've seen those twisted torus knots, you usually take a torus knot and then you take a smaller number of strands and twist those up a bit. So indeed, we've got some examples of T-links here. If you've only got one pair of integers, then you get a torus knot. This is shown on the left. In the middle, you could kind of think of this as a generalization of a twisted torus knot. So you've got you take your torus knot 7, 5, and then you grab, in this case, 5 of these strands, and you take 3 overcrossings of those, and then you connect everything up. Or you can take, in this last one, you've got 3 pairs. So you start with this previous picture, only now you add, you grab 3 strands over here, and then you put in 4 overcrossings over here. Okay, so this is a T-link. And to show that these are equivalents to the Lorenz links, this is from their paper again. They started with the template. Your knot is on the template. They kind of just unrolled the template, and they ended up with these braids. There was more work than that went into it, but it was I think, a very clever observation. And this is from their paper. Every Lorenz link is a T-link. Every T-link is a Lorenz link. And then they said this a little bit more precisely using some notation in their paper that I won't go into, but that's the main point. Okay, so we can use T-links instead of this Lorenz template where it is convenient for us. And it is convenient for us. So the next part of our construction is this very cute 4-page paper by Sang-Yap Lee in 2012. He showed that if you have PQ, any coprime integers, 1 less than P less than Q, and then you take some integer K with 1 less than KQ less than P, then a twisted torus knot, which in T-link notation looks like this, so TKQ, KQS, comma PQ. This is going to be a particular cable on a particular torus knot, okay? So maybe just to draw this a little bit on the side, if you've got a PQ torus knot here, so P strands going in, Q strands going over, you grab KQ of the strands, and then you twist them around each other S full times. So that'll give you KQS over crossings. And then this is going to be a satellite knot, and it's a very particular satellite knot. It's a cable on a torus knot. Okay, so this is Sang-Yap Lee's 4-page proof, condensed into a even shorter talk. So this twisted torus knot is obtained by 1 over S Dane filling on the red link component. So what have I done? I started with the PQ torus knot over here on the left. Well, this is Lee. Lee started with the PQ torus knot. He augmented it with this red link component. And when you do a 1 on S Dane filling, then you will end up with the T-link that we're looking for. So rather than doing the Dane filling, what we do instead is we start dragging this little link component around. So we're going to start over here, and we're going to pull this component of the link, just a little segment of it, pull it around, all the way around the knot as shown here in the middle. But then when you do that, you can use the fact that there's a meridian of this Hagard torus to untwist a bit of this red thing. And that's what has happened in the middle. So he dragged around a bit of component all the way to where to 3, I guess, is the, so it came over to here. And then he used a disc like so to untwist this whole thing and to get this link in the middle. Okay, and then he did it again. And the trick is, because we are encircling exactly some multiple of Q strands, this K times Q strands, after you do this K times, you are going to end up with this nice connected, basically it's a K1 torus knot is what the red has become. Okay, so and now if you look at this carefully, you can see that we can push the K1 torus knot into the torus on which the PQ torus knots sits and make them disjoint. So there will be a Haggard torus for S3 that's separating. You've got the PQ torus knot on the outside, you've got the K1 torus on the inside, and this that will give you an essential torus in this original link complement. Okay. All right, so then we're not quite done. So we can be a little bit clever with this. So this, I've sketched here this Haggard torus now in purple. And I haven't drawn the PQ torus knot on the outside of it, but you can think of it, there's the PQ torus knot is sitting on this purple torus down here at the bottom right of my screen. And then what you do is you take your head, which is looking outside at the PQ torus knot, and you move it to the other side of the PQ torus knot. And this is a well-known transformation. You get a QP torus knot, and that looks something like this, and now is enclosing the K strands of the TK1 as shown. Okay, so we're going to ignore for a minute the fact that we have a QP torus knot on this link component over here, and we're just going to call that C. All right, so now jumping back to Lee's figures, we have our K1 torus knots, and we have our link C that's got a QP torus knot invisible on top of it. You can switch the places of these. So you can do this basically following the same procedure that I showed you above. If you want, you could just drag the strands of C around and then undo, and you get, now J becomes an unknot encircling C, sorry, is a K1 torus knot. And everything I've done here is an isotopy to get my original knot. Then I do a 1-on-S stain surgery on J. And what does that do? Well, remember on C, hiding on in a neighborhood of C is this TQP torus knot. So when I do the Dane twisting, it just twists up that torus knot, and we get C becomes the companion, this becomes a torus knot, and then the pattern is this QP torus knot with this additional twisting that comes from performing the Dane filling on J, and that's the full proof. Okay, so I think that's quite clever and quite fun. So my observation with Tiago is that you can extend this to T-links almost immediately with multiple unknot components. So this is a picture from our paper. It's a little bit messy. I need maybe a bigger image to show that, but the same sort of idea happens. Anytime you have unknots anywhere in this diagram that are enclosing a multiple of Q strands, then you can pull them around kind of simultaneously. So I did this on the opposite side of Lee. I've got, if you start over here with the red strand and start pulling it around, so you pull it around the diagram, and then the green strand also is in the same region, pull that around as well while you're at it. And then we can use the fact that there is there's a meridian here of the knot to untwist the red and to untwist the green. But this time, because there are two of these coming in together, they get twisted up a little bit. So you add a little crossing here. However, notice it's still completely separate from the black, is the original PQ torus knot that we started with. And so you can carry on, and you can do this with all of these link components. And when you're all done, you get this link now, this kind of that you can push inside of the torus on which your torus knot lies. Okay, so the black link is the original torus knot, and then we've got the colored links, and these are separated now by what's going to be an essential torus. Okay, and now do the same thing. So we have put your head onto the other side of the torus knot. You get a TQP sitting on top of this purple link, and we can drag the purple link around to obtain a torus knot that doesn't interact with any of these other things, but then slowly drag them back and put them back into position that looks like so. So now we've got my original colored unknots are bounding this companion torus basically in this unknotted fashion. And so then we can do the Dane filling independently, and we end up with a cable knot again. But because of the fact that we now get multiple of these unknots to work with, it means that we can make the companion a different T-link. Okay, so we've turned our companion into a T-link. So far, this is not a counterexample to Morton's conjecture, because Morton's conjecture was that your companion is a T-link, reinterpreted in the T-link notation at least. The companion is a T-link, the pattern is a cable, and this is still, we still have a pattern that's a cable. So the observation to make this, to break that conjecture is, when we undid all of these twistings, we did not touch these are the Q strands basically that are going up and over the torus link. So all of my, maybe let me go back to Lee's figure just to make that a little bit more clear. So every one of these moves, when you're untwisting these things, they avoid these, a region like so. They all go around something. So I can put any tangle that I want into that particular site. And so we put any tangle we want. We're going to replace it with a braid corresponding to a T-link to get whatever, basically whatever T-link we want inside. Okay, and so then to prove the fact that we can get a hyperbolic link inside and out, well, now we can basically make any T-link we want on the outside and nearly any T-link we want on the inside. There's some extra twisting involved. But what we do is we choose our tangle to give a hyperbolic twisted torus knot, really is what we want. And this, there's a lot of work on which twisted torus knots are hyperbolic, particularly due to Senyap-Lee again. So you can do that on the inside and the outside due to work of Lee. And then one of these is going to be augmented. And to get that that's hyperbolic, you then follow that by a theorem of Ito. Okay, so that's it. That's the construction. As we discussed this with some other people, we realized that the original Berman and Williams construction also would work well. So here's another second construction that we came up with. This is from our paper again. Rather than going through all the I think that it's harder to absorb the words here. Let me just show you the picture. We're trying to build satellite knots. So let's just start with a tube. And we're going to insert into this tube our favorite twisted torus knot, basically is what we do here. Now I've done a bit of cheating. So a twisted torus knot would start out with some sort of a tangle in a twisted torus knot up here, and then we would have a PQ torus knot here. And I have moved the tangle around to the bottom. But then once that's done, I carefully insert a T-link into this tube. And by careful choices of parameters, you can see that you can just fit everything inside a tube as desired. So this is now my outside. My companion is a torus knot. My inside is nearly any T-link that I want at this point. But then you can adjust this construction. You can take the outside, turn the outside into whatever T-link you want as well, just by adding extra twists of the tube up here. Okay, so nearly any T-links on the inside and outside, not all. So some open questions that remain from this work that is, first of all, well, the Lorenz satellite conjecture, the upgraded Morton conjecture, Morton-Berman-Kaufman conjecture, maybe we can call it. And then another conjecture is, if you're given any two Lorenz knots, then can you, if you take the satellite with pattern K and companion, pattern K1, companion K2, is this always a Lorenz knot? And based on this construction, this previous construction, it seems that the answer is possibly yes, except we have to twist up our pattern a little bit more in order to fit it inside. And so if you don't allow that twisting, it's not quite clear that we can get everything. But anyway, I will stop there. Thank you.
Okay, thank you very much. Oops. Are there any questions? No questions.
Actually, just one. Could you scroll back to the just the template? I'm just in my mind. I'm trying to knot it up, but I guess that doesn't work. Shouldn't work. Oh, it's that
This one?
Yeah, okay. Yeah. No.
Yeah, and this picture from Berman Kaufman may be helpful too. So you always go, if you're going to the left, you go over. If you're coming from the right, you go under.
Mm-hmm.
And then you just, whatever closed curve you can draw on that is going to be a Lorenz knot.
If I just sort of cut, I don't know, let's say, I mean, cut and reattach, right? So just take like the left loop there and chop it open, tie it up, and reattach. Oh no, but that's not a Lorenz companion. Yeah, I see. Okay, neat.
Yeah, there are generalizations, I think, to knots on other templates where you have different branch surfaces, and look at that. But I don't know much about that.
Mm-hmm.
But these knots really are some sort of orbits that show up in some sort of dynamical systems, right?
Yeah, that's right. Yeah.
Mm-hmm. So, but is there any example of satellite knot that is not Lorenz knot?
Yes, there are examples of satellite knots that are not Lorenz knots. I think Berman and Williams actually have examples in their 1983 paper. I don't know them off the top of my head, but yeah, so Lorenz knots are actually quite special. They're all fibered, for example. So yeah, so they're not extremely common. If you enumerate knots by crossings, for example, you're not going to see very many Lorenz knots. Surprisingly, if you enumerate them by tetrahedron and the complement, you actually see lots of Lorenz knots. It's one reason I became interested in this problem. They're somehow more geometric than combinatorial.
Okay. Yeah, but if you change the template, maybe you get different knots.
Yes, yeah. Yeah, and I think that that was a follow-up. I think that Berman and Williams started looking at some other templates, and they actually found that with different templates, you could get every knot. So it became less interesting, possibly, for different templates.
Yeah. Okay. So, any more questions? Or if not, thank you, guys. No?